that we've been...
Cliff is too generous. Cliff has been hacking since his 8th grade. And, has probably hacked on every known hardware machine that we've seen. And I happen to have my, I would say, synchronous lock on him and able to put him to solve the problems of math. Essentially bring a math engine into the open source land that we can use, normal humans can use, and apply and extend. So here he's, now you've already seen one genius take the stage. The second genius is here, and we'll see how they compare, the R's GBM versus H2O's GBM and our understanding of how to extend it. So without further ado, let's click.
Thank you. Okay, so I want to give 10 seconds about H2O, and then I'm going to flip to demo, and then we'll flip back to the rest of the talk. So, HexData is building a thing we're calling H2O. It's pure Java, it's open source, you can download it from the Git, and it's a platform for doing math, in particular parallel distributed math. We're trying to solve the world's problems that we can do fast and efficiently. So what fits in memory? And we have implementations for generalized linear modeling, distributed regression, GBM, random forest, and so on. It's drivable from REST and JSON. And in fact, we have a nice R wrapper, which I can demo as well, especially if I get, not in a minute, we'll pull that one out in a minute. I'm not an R hacker, so I need the in-house R people to come help me drive. And it has a bunch of the cool stuff inside. And so before going more into the insides of H2O, let me see if I can pull a demo up. So what you didn't see here, let me see, where's the good, here we go, we'll do this one here. So this is a couple screens from showing H2O, and here we have a cluster status page, and the thing to look at this is it's a 16-node cluster running in EC2. And somewhere buried in all the numbers and whatnot is the amount of free memory involved in each machine. It's about 25 or 30 gig heaps. Free disk space, CPU, they're all idle right now. A bunch of other interesting stuff for a cluster status page. With this cluster, I loaded the airline data set, which was 123 million rows and 31 columns. H2O is a column compressed store, so after compression, it's in memory in about 5.87 gigabytes, representing so many columns across here, however many it is, and 123 million long. Goes on a long ways here. I jumped to the bottom, and the row numbers just keep going, so fine. So it's a lot of data. With that, I ran a GBM, and this version was run with me taking like default parameters, so not necessarily the best, and it got cut off, but there's 100 trees or so there. So I didn't run it long enough, and my stumps were a little bigger, and my learning rate was too big, and there was a bunch of other issues, so it's not necessarily a great model. But while Trevor was talking, this was running away in the background on my laptop, connected EC2. And so sometime in the last half an hour to an hour, we have a GBM model built on 123 million rows of data. So that's by itself an interesting let me do one other quick test here, and I think I'm still running this one. Look, you know, my laptop is complaining because things were, because it went to sleep in the middle. So here, I will from scratch. I'm going to kill my Java here. I'm going to relaunch. So I just launched a Java program. It's on my laptop, so it's a cluster of one node all by its lonesome. And if I come back up here to the GUI, I can find that I'm poking around. I'm pulling up something here called GBM. Oh, the font is way too small. I wonder if I can do this on the fly, or I should just do it up now. It's going to work. That looks better. Okay, fine.
Bravo.
Right. Pull some data in. So this is a tiny thing here. It's 1,000 rows. I'm going to flip to another tab, which I loaded earlier, but I just killed my guy. This one says eval instead of model. And so I'm going to load this guy in. And I've got 2 data sets loaded. I'm going to go back to the first one, run distributed GBM on my laptop here. Pick the, I don't know what ANCOS is, but that's what we're trying to predict here. Exclude the site number, which is a unique ID. If you have unique IDs in your data set, you go do a predictive model. They're stunningly good when they pick the unique ID. Okay, so then here I'll grab, where'd it go? There it goes. The eval set to do validation on, and I'll just hit go. And so this is just running on my laptop here, and we're pounding out, I guess we're about to be done here. I didn't pick enough trees or something. So one more hit, yeah. It's done. Okay, there it goes, fine. So anyhow, I just ran a tiny model using GBM. So we have something that works. It runs on a laptop, it works on a big cluster, it works on tiny data and big data. It's actually reasonably fast on small data and quite fast on big data relative to sort of your other options in the world. So then I'm going to go in and talk about what it is and how it works. Okay, so so the talk's kind of broken up. So I'm big shift from Trevor here. I'm the systems engineering guy, not the math guy. I've spent the last 1.5 years getting my math head put on, but my intuitions are just not up to where Trevor's at, and so it's always fun listening to him talk. But I'm going to go ahead for systems engineering for a little while, and I'll bring it back to GBM towards the end. And so the first thing I have to think about when I'm looking at engineering any of these math problems is talking about big data, where when I say big, I mean more than what fits conveniently on one node. So we're immediately into the realm of distributing. Some of the data is on this node, and some on this, and some on this, and we have to do some communication between everybody, and how do we discuss that communication, how do we describe how it works? So the building block in H2O is what we call a vec. It's a distributed vector, like a Java array, but the length is more than 2 billion, perhaps. So the length is listed as a long value. There's fast random access to any given element in the array, and the notion of missing data. So the is and a is the same as are. And the variable size I can append, I can grow vectors of power, size, and shape I want here. Internally, I'm going to do a whole lot of stuff with this data. In particular, I compress the bejesus out of it, and I do math in the compressed form. That's transparent at this level. You just say, give me some data, and your promise is that it's fast. If you code to the style I'm about to go to, it will run parallel and distributed as well. Although if you don't, then it'll still work. It'll just, you won't be able to go parallel. And if you're talking about 1 billion rows, you know how to do that. So fine. Okay, so with a vector, it's like an infinite huge array of some sort of primitive, usually double. But then we have a collection of vectors that's more interesting. So a frame is essentially very similar to an R's data frame. It's a collection of however many vectors, and what I promise you is that the data is distributed, but not randomly. It's very carefully co-located across machines. So I'm showing 4 JVMs here, for example, where the data has been striped across machines such that the vectors all co-align. And what that means is that I can refer to any one row on one machine, all with good latency. There's no network traffic if I'm going across a row. Within those chunks of data, within the data on those machines, I break it up further into chunks, where chunks 1,000 to 1 million elements, depending on compression strategies and other things. The actual size doesn't matter at the programming model end, but the key is it's a unit of parallel access. When the algorithm is actually written, your expectation will be you're going to run over 1,000 to 1 million elements all at once on all the rows and however many columns you've got, right? Getting and putting data, reading and writing is going to be a few clock cycles, just like it's a Java array. It's really fast. That's including the compression. So generally here we get into like memory bandwidth bound issues, not CPU bound. So unit of parallel access means that when we actually do math, all the chunks go run in parallel across all the machines and all the CPUs light up, and we get, the H2O internally handles load balancing. You get fine-grained data parallelism. And a MapReduce paradigm coming up is going to describe how the communication goes when you have to cross the boundary between JVMs. And that's all managed by H2O. So, overview real quick. A frame is a collection of vectors. A vector is a collection of chunks. A chunk's a collection of 1,000 to 1 million elements, kind of varies. Or an element, conceptually Java double, although how it's compressed in memory varies according to your data. In particular, if you had a Boolean featured variable, it will be a bit vector in memory, unless it's actually very, very sparse, and then there's even more compression going on into it. Fine. Okay, so there's a couple ways to talk to this kind of machine. If you're going to do whole algorithm levels or whole vector math, REST and JSON work out really well, and this is how we talk to this guy from like R, from the R console. So we might say, load a data set, run a GLM or a GBM on it, do something else that's a mess with whatever you're going to do with it. So that's the whole algorithm, whole vector in motion. And here you're just like poking H2O with a URL and getting a JSON response back that said, do it, here's the answer. Then if you dive into H2O, you can now do your own math. So that's great if you're, the first solution's great if you can talk at that level and get the performance you want. If you're doing something that's not what we already have built in, you might want to write your own math, and now you're getting into the simple data parallel coding, which we're about to head into, and it works really well for problems that look a lot like any sort of dense linear algebra or dense walk over all the data and do something. And then there's more complicated things you can do if you want to really get nuts and boltsy here.
Join our kit.
And join our kit and find out all kinds of cool things are going on. Okay, so now we're going to get into simple data parallel coding. I'm going to ramp up these examples very gradually, and then we're going to turn off left and go look at how I implement trees, distributed large trees over distributed data sets. So the simplest case here is I'm looking at basically a stateless computation. I'm trying to compute some in thing that requires me to visit all the data. And there's two interesting calls here. There's a map and a reduce. The map takes something of one type and produces something of a different type. In this case, they happen to both be called double, but that's not the general. There's more general than that. The reduce takes things the map produces, takes pairwise of them, and reduces them to 1. So it's a 2-to-1 reduction in a reduce step. In this case, I'm going to pull my data out of some vector. At the bottom I say do all. I hand it a vector, I get a double out, I'm going to do something with it. In this case I square it, return it, the reduce takes pairs of those and returns that, fine. What will happen here is these lines of code will give me the sum of squares distributed across the cluster for just a handful of lines of code. So it's pretty straightforward to get this. So I can go on and get a more complicated example. So in this case, I'm going to get state, and state means I can accumulate all kinds of goodness and crazy things going on here, including having all kind of arrays where I'm writing into different kind of buckets left and right. In this little simple example, I'm reading from 2 vectors and outputting 3 values, which is the sums and the sums of squares. And really, conceptually, map is taking some collection of primitives in and producing this pointer out. That's his return result. And the reduce is taking a this and a that, 2 things of the same class, and folding them together. And the promise I'll make you is that map call will run single-threaded from your context, although it'll be running in parallel in different data all over the cluster. And the reductions will also be running single-threaded from your point of view, but they'll be doing logarithmic tree roll-ups, and some of them will be happening over the wire, although that won't be visible to you. So the fact that it's across the cluster isn't visible here. You just know that I get reductions pairwise within a node, and then the reductions go across the cluster pairwise until they roll back to the original guy. And the actual use case here, if I say make me a new LRPass1 object, go do a do all, that new object I just made holds my final result. So the data was all over the cluster, but it came back to the object I just made. It's a pretty straightforward programming model. And I can show you actual code. These are all like abbreviated as a fit on a slide. I got my Emacs here, I can show you the actual code. And it looks very, very close to this. Okay, a little more complicated. I mentioned things were chunked, and the chunks was a unit of parallelism. So if you don't do a map, if you do a map the way I showed in the prior slides, there's a for loop around it for the whole chunk. Here's the for loop that's exposed. And the reason it's exposed here is because I might want to do something that's loop invariant within 1,000 to 1,000,000 things. So the loop invariant piece of that means I get some batch level efficiency gains going on here because I'm saying 4,000 or 1,000,000 things. And passed into the map or whatever my data chunks are for the vectors that are going through. And then I do a for loop over the length of the chunk. That's however many elements are in that chunk. The cx.at, cy.at, those are doing the decompression. They're pulling an element out just like a vector, give me a value out of an array, right? And I do my math just the way I did before. The reduce and the rest of the map are identical. So this is sort of a straightforward thing here. Is that, we all kind of good at that level? Okay, so now I'm going to jump into GBM here. So this is the algorithm we implemented. Elements of statistical learning, page 387. Nice eye chart. Trevor covered it really nicely just a minute ago. The thing to look at is step 2BII, fit a regression tree. So all the time and expense in this algorithm is like fit the regression trees. And everything else comes out fairly cheaply. So that's the part that we're going to do in parallel and distribute it. So now I'm going to switch over to distributed trees.
How many times did Trevor make sure we are doing the right thing?
At least 3.
Okay.
So yeah, there was a number of interesting conversations with Trevor where we got the idea, we went and we implemented something, and then we came back and said, hey, what about this? And he was like, what? What are you doing? Wait, back up. And they were like, oh shit, we'll go back, try again. And we went a few rounds, we got it right.
Actually, some of the things you were doing were very interesting.
I'd like to think I'm a smart guy, but just don't necessarily have the right training to read all the math. So I invented what I didn't understand. Okay, but what we have now is out of the textbook, straight up, although maybe there's other interesting algorithms floating around nearby. And someone ran off my water, which is neat. Okay, so what I'm doing with the distributed trees is I'm really leaving the data in place, and I'm going to break the data up into the splits of the tree, the little leaves that come at the bottom, by assigning a number to each row saying where you are in the tree. And the rows and the observations, they're all wherever they land in whatever node and whatever tree. So the nodes don't have a collection that I can conveniently say, these are all the rows that are in this node, do something with them. Instead, the nodes, the observations just stay put. But when I go visit an observation, I can tell you immediately, in small constant time, what node it belongs to in the tree of the moment. And then I'm going to use that to compute something interesting about the node. And after one pass over all the data, I will have visited every row, and thus every row for each leaf of the tree, and have computed something for that leaf. Then I'll do something with those tree leaves. So pictures. Okay, so here's an example. I have some initial tree, and all rows are pointing at node 0. So on the right, I've got a column I've called nids. So if I'm back up here a second, I said v.make0 nids.set blah, blah. Okay, what I really did there was I said, make me a new temporary vector called node IDs. It's an all 0 vector, which means that it compresses infinitely well, and this call is essentially free. So a billion rows doesn't matter, that's like freebie, I gotta buy those zeros. And then everyone I'm gonna set to what node ID, but it's a 0 vector, so everyone's already set to 0. So that's my initial state, really cheap. I have some x's I'm going to use to, as my feature, and I have some y I'm trying to do something with, trying to predict on maybe. And I run some MapReduce tasks there, and I compute average and variation, right? And I'm using that information, whatever I'm gathering, to decide how to split my tree. And the actual split decision varies by algorithm, and different people are doing differently. Here I'm going to show an example where I'm going to do regression tree using, I'm trying to minimize mean squared error. So I'm finding the best column, best split point to minimize MSE. Having decided I want a decision like if x is less than 1.5, go left, else go right. That implies a split over the data, but I haven't done it yet. It just implies a decision at node 0. So on the next pass, I visit every observation and decide, oh, you were at node 0, that decision is left or right according to x is less or greater than. Okay, now you went to node 1 and node 2, and I update what leaf you belong to, and then I throw you into the math for that leaf. So then I get a new average and new variance at the end, having built an entire layer to the tree. And if I go it again, every layer, every pass of the data adds a new layer to the tree. So pass by pass by pass, I'm adding a layer and splitting as I go and getting predictions as I go, however I want to jam the predictions in or whatever. These all vary according to what kind of tree builder you're doing. So the summary is each pass is one layer in the tree, and it's some combination of map and reduce calls that are going to do the work here. Here's a sample map for this tree algorithm where, reading it line by line, I'm going to go up here, I'll play the game and get on stage now. So there's some node ID I'm pulling out. This is the collection of them all for this chunk. For all rows, pull out the node ID for this particular row. They're all over the map. Make sure I have a histogram available to me, and then go ahead and accumulate where this accumulation for the MSE style trees is computing mean and variance. This is what for the columns in question all the way through. So as I run through the data, I end up with a histogram for every leaf, which is the mean and variance, but I actually have a collection of one for every column, for every leaf, for every tree that's getting built. Fine. Once I got a tree level, I use that those histograms to decide what the new split decisions are. I assign them to the tree. That's just a plain old Java object. I just run through the Java object and say, you have a split decision, left, right, whatever it's going to be. And then I go again. And the thing that I don't need to screw with or think about is that tree now gets passed around to the cluster. Everyone uses that tree as an input. It's just another plain old Java object getting passed around, and it's driving the next split decision, and I go layer by layer by layer. Conceptually, I'm scoring and building in one pass. I've mentioned that already. I have a couple of utilities there. I can score a tree, which I just take an observation and pass it down the tree, or some collection of trees. The trees, as mentioned by Trevor, you might have hundreds to thousands of them. If they're stumps, they might be small. If you're not stumpy and you're looking at a GBM style tree, it grows, it doubles in size basically at each layer. They can go quite large, so we compress the bejesus out of them, get them quite small. All kinds of fun utilities for walking, printing, displaying them. And I can show some of those in a few minutes here. So one of the things that has been commented about GBM is it's not parallelizable because of the nature of your building the second tree from the residuals of the first tree. So what I've done is I've not changed that, or I've not worked around that magically or anything. Instead, what I'm doing is I'm parallelizing it through the data. So there's still a latency issue, tree by tree by tree, row by row, layer by layer by layer. That's still single-threaded, if you will. But at the point between each layer, that goes fully parallel to compute the map. So I can keep adding more data if I keep adding more compute nodes and keep my tree building time constant. Otherwise, it's pretty classic GBM using the algorithm shown on the prior slides. I think I'm running low here. Oh, speed. So we're seeing somewhere between 2x and 8x faster than R on a single node than the C++ version of R on a single node. But we can scale out by adding more nodes, and that lets us pile on more data and maintain the good speeds. I think as we get, if you get a single large machines running R, I'm seeing that we're actually substantially faster because we're also multi-core on one machine, and so we'll light up all the CPUs and have it go to town.
Is that 4x on one core? Does that come from multi-core?
4x on my laptop, so that could be multi-core. So you're looking at C++ versus Java implementation. Otherwise, I suspect the implementations aren't too far from each other in that sense. So I would kind of like to believe that it's 2x faster node CPU to CPU, but I haven't done the math and I don't know. But I see that when I go, but I can't buy a one-core machine, right? So I'm always getting at least 4 on my antique here.
By the way, if this GBM is slow, it's a bug, so you'll fix it.
Yeah, I'm the performance guy too, so if it's slow, it's my fault. Okay, so the summary here, this is really quick. Most simple Java just works, right? So you can just read and write Java code in those inner loops with the caveat that you're doing this map and reduce. You keep that mindset in place, and all kinds of code can be in those loops, and I have tons of interesting examples. And then it runs fast. Reads are basically the same speed as plain Java array loads, despite the compression, or maybe because of it. Writes are a little bit slower because I will compress behind the back. I follow the full Java memory model rules. So if you start doing conflicting writes, that's how the ties get broken, but that may not be what you want. So I'll claim that I do the right thing, but maybe you're unhappy with the results anyhow. And we support some transactional updates, which we use internally for all kind of control management situations. There's lots of those going around where you just need an atomic, no one mess with me, I'm just going to do this thing kind of stuff. So we're writing analytics. This is a wrap up here. Generalized linear modeling, logistic regression, Poisson, Gamma. These things have been running for quite a while. GBM and random forest, k-means, k-n. These are all state-of-the-art algorithms. We're trying to pick the best of the best of the best for algorithms, and we have them solidly working on 100 gig data sets, and we're heading upscale. And
we're actually only picking algorithms that customers are using, so new users join, we'll pick new algorithms.
Okay. So instead of going to the
R demo.
yeah, exactly. I said right for the R demo. So instead of going to cool slides I don't have time for, let's switch to our demo. And maybe if Angie wants to come lend me a hand. Here, let me shrink some windows. Make sure I do this right.
Very few Windows users.
So everything else go away. I'm going to launch RStudio, and hopefully mostly from scratch. Where it goes? Okay, so we're here, and I need to start installing packages, right?
Yeah, so the first thing you do is install the H2O R library package.
And so I have, I'm sorry?
Can you increase the font a bit?
Yes, let me try doing that. And I actually don't know how to do it in RStudio.
Views.
View, zoom in. I knew I got a PhD for something. And I said that, and I'm not getting a whole lot. Oh yeah, we're getting a little font right there. Okay, fine. Is this better, or go one more?
One more.
One more. Okay, that means everyone wants at least two more then, because I heard too many one more.
That's good.
Okay, now it's more. Okay, fine. Okay, so install packages. Browse. So this is grabbing the tar file which you can get from our website. In this case, I'm grabbing one from my local build because I live dangerously and I have the latest and greatest. I just built it yesterday, well, this morning. So
Possibly go wrong.
exactly.
Now,
Hopefully, I tested this once before I got here and it's not going wrong yet. Okay, so I did that.
So
Now
this is
what?
now
transparent.
so you basically do library or require H2O, you just
Aha.
click the little box.
Okay, so I click that.
Yeah,
Okay.
load in the library. Okay, so then the first thing you do is you install the dependency packages,
Aha.
which is
Click in here and H2O.
H2O.install, you can tap complete that.
Tab
There we
complete,
go.
okay.
And that will be for parentheses.
Let's go.
And all this does is it installs and makes sure you have certain R packages that are required to run H2O R package. So R curl and R JSON are necessary because you're communicating through the REST API.
Okay.
Okay, so that's done. Now you just initialize. So you need to make sure H2O is running on your local machine first before you type that.
Okay, so my H2O is running in my Emacs buffer here, and it's showing the results of the last GBM's output.
Assign it to
There you go.
Da-da-da-da-da.
Installing. So what that did was that basically communicated with H2O and got the correct, there's like R methods, loading the R methods that are needed to communicate with that version of H2O that's running. So there, it's done. It
Yeah.
tells you, okay, I'm connected to H2O on, 127.0.1, and now you can start running demos or read through our help guide, so.
Okay,
let's
so-
run a demo.
Demo here, H2O.gbm. It's the obvious demo, right? Okay, I think the viewing has confused RStudio. Okay, so here we've loaded prostate, and it's loaded on my H2O cluster, and this line here looks like it has done something with iris, and run on the cluster, and I've got some mean squared error per tree output, and I've produced GBM models for prostate and iris. And because I don't want my email to go away, I want this. Okay, so this is running on 127 here. I'll clean this off here. 120 is my local H2O cluster of size 1. View all. There's some GBM models. There's an iris got loaded in there. I'm looking at. I will go to this guy here real quick. So there's an iris data set. Where's my GBM model? So let's click for a GBM model here.
Probably just look at the most recent.
Oh, and this, which one?
You look at the most recent jobs.
Oh, jobs. That's probably the way to go. Oh, running jobs. Okay,
Yeah.
fine. Look at they all ran.
So this is like.
And bang. Okay, here we go. So I have a confusion matrix, and I ran GBM, and there's a little yellow warning that says that the confusion matrix is being reported on the training data. So caveat you go there. But the iris, you expect a pretty good result out of. So that was run from R.
How does that look in Java? Is it one?
Yeah, let's play that game. So here I have a button that says, show me that model as a piece of executable Java code. So it's a big model because there's 100 trees or something in there. But if I own 10 trees, but so I'm doing regression trees. I'm going to step through this code here a bit at a time. Here's my columns. They're all very boring because I grabbed an iris data set, didn't have any headers. Fine. It's a 3-class model. Okay, fine. I have a function called predict, which is going to take an array of data and return me an array of answers, a probability distribution, where 1, 2, and 3 are the probabilities or the the values that the trees produce for class Virginica, Setosa, and whatever the other class in Iris is. So for the first tree in GBM, the first guess to get class Setosa is if data 2, which is like petal length, is less than 2.45 millimeters, then you guess 0.4, others you guess minus 0.2. Fine, there's something there, right? Same thing for versicolor now. Here's a more complicated tree right through here. And then there's a third tree for Virginica, and those 3 trees together make up what I'm calling tree 0 for the first GBM tree. And I have three regression trees producing, I think it's log likelihood for each of the different classes. And then outside of this predictor, but in the boilerplate, there's something that rolls them together and turns it into a probability distribution and a prediction for the max probability got, right? And so that's all done in the boilerplate. But this is the output of the regression trees for GBM. And in fact, the fact that there are 3 trees and they're combined fall right out of the algorithm we saw from the elements of statistical learning.
So you could take this to production, that's it.
You could just cut and paste this and go with it. It does scroll on a ways, so you probably don't want to eye chart too long there. Actually, since Iris is so predictable, yeah, there are a lot of places where I just get a 0 because there are just no more errors to clean up. Iris is just too good. Okay, let me collapse this guy again here. There's another fun button. Here we go, go away.
Did you have to write all this code yourself, or did it generate that code?
I'm certain that I did not type all that code. No, it's auto-generated. So internal into H2O, we have these models, and they're represented as some sort of tree format. Well, we have a tree walker, and we can pre-print the tree in a variety of ways. One of them is to pre-print it as Java code. But we can pre-print it in like a nice little text way. And we have not hooked up to GBM yet, but we have internally one that makes it into a graphical view. So you can actually get you have to have graph viz loaded, or get one of these tree node and edge drawers, and out and your browser pops like a tree. Which works great on Iris-sized trees and kind of sucks on like the giant trees you get out of random forest. You get an eye chart of like, we can also ask for the contents of the page as JSON, and this is what you get if you just, like up here it says GBM model view in the line and .html. If I say .json or click this JSON button, I get the same thing as JSON. So this is part of the REST URL. So all the things that come out from the JSON side of things are all machine generated. So we're not trying to keep in place multiple ways of the GUI versus the JSON versus the Java. If it's written in the Java code, it is out in the JSON as well. So that's the guarantee you get from the auto generation of stuff. GBM grid, it's a good grid. Okay, so here is a model that data was loaded, thank you, Angie, very much. Here's a model loaded by Iris. I don't know how to run GBM grid from R, so I'm gonna run it right here. Model GBM, Iris, we'll take this guy. Response column is 4, I'm not gonna ignore any columns. Okay, so for gridding, here's all my arguments. I can pass them in on the URL command line. That's exactly what R is doing. I can pick things and separate them by a separator, and I'm going to roll over that, iterate over all those combinations, right? And then here's, I'll pick a learn rate of, and small learn rate. Okay, so I got a bunch of things. I get a different page, the GBM progress page. You can see I'm like screaming along because Iris is too small here, and I've got a bunch of models that are perfectly perfect. And it's just going. So I don't know, I picked 100, it's almost done. But this is grid search over your parameters, done just like that. So there are some parameters that suck, relatively speaking, but some that are doing fine. So let me go pick a different data set here. I think I had one, yeah, I had an ecology set here, so let's just, where's the run GBM? Okay, we're going back up here. I'm going to switch to a different data set because I want to demo showing the confusion matrix on test for and train here. So I have an ecology set, and I have a model, and I have a, let's see, this is on house, ignore site. And then in the validation, I'm going to put in the eval set, and then I'm just gonna leave the other arguments alone and just hit go again. And so what happens here, let's see if I can drill into another page here for a second. Oh, my laptop's getting hot now. Okay, so here's a confusion matrix built on the ecology model set, but evaluated on the eval set. So it's not getting, you know, so perfect an answer, as it were. If I go back to the grid search, you can see I'm rolling along, but I seem to have probably topped out at 14.6 error for this particular choice of parameters here. Crunch, crunch, crunch. So I do have 4 CPUs in here if you're asking me, you're wondering about that. So he's doing some 4-way thing, and that's what he's getting hot somewhere. You can hear him get louder now. But he's almost done here. Yeah, I think we topped out. Yeah. Okay, fine, we topped out. And then, oh, come back. There we go. And there's my model. Well, there's my prediction, my confusion matrix for that particular model. I can also evaluate data sets and get you know, prediction vectors, which are what drives the confusion matrix out. You can dump this data out, in and out as CSV format. We pull in data from EC2, obviously, S3, Hadoop, HDFS, local file system, distributed local file system. We run all these things, all the I/O is running distributed. So if you have the data distributed in some kind of distributed way, we'll read and write it distributedly as well. So you get the I/O bandwidth things. So I think that's the basic demo. And
You can do questions at the end.
you want to go to your recording next, and then we'll do QA at the end? Okay. Okay, we're going to take a break.
Oh, the Java? I haven't written that in, but if it's something that people want, I can really add that.
It's got an on-off switch or turned on?
You can certainly go into a web API and find it, but R will not be able to return it. R will just return the keys.